next session here, I'd like to introduce Dr. Bill Burgos, who's been working on a project that both PA AMR has been working on with the Shamokin Creek Watershed and Tetra, and Angela Mack down in the anthracite region, way east of here, in the Shamokin Creek Watershed, to talk about some work as they're trying to figure out what is it that they're going to need and how many treatment systems are going to have to go into place, and how do we deal with the water quality issues in AMD that have historically been impacting the Shamokin Creek watershed. So I think Bill's presentation here, which we've done at some public meetings already with them in the past, will show you a little bit of the extent of the work that's gone on in the data collection and the background and development side of things that we've been working on with them and they've done for Shamokin Creek to get this plan together, basically an assessment of that watershed to see how they can prioritize some of the sites in the watershed. So Bill?
Thanks, Bobby. And thanks for folks staying towards the end of the meeting. So my name is Bill Burgos. I'm a professor of environmental engineering at Penn State, but I'm working part-time for Tetra and really enjoying the sort of practical side of things that I'm learning about on the consulting side. So we'll talk about the Shamokin Creek watershed and so have images of a big breaker as far as extensive coal mining in this particular area, leading to extensive environmental impacts as evidenced by the orange streams that predominate in the region. So the Tetra Tech project was to collect the most recent data with respect to conditions on some of the major discharges, review and synthesize it with what has been collected previously, and then basically recommend to SCRA, like what are the grants and come up with a prioritization plan with respect to restoration efforts. And there's a lot of collaborators here. PA AMR did all of the field work with respect to measuring, collecting water samples and doing the chemistry on these discharges. Conservation District, funded by DEP, and SCRA is our client. So what I'll start with is just going through some of the current conditions and give you some pictures of these different sites. First of all, we have the watershed itself. So there's an inset. We are upstream of Harrisburg, town of Sunbury. The purple boundary is the physical boundary of the watershed. The gold boundary is the physical boundary of the coal regions. And the red lines within the purple boundary are defined as impaired by the state with respect to having an absence of a fishery. And what you see is there's this so-called upper watershed, 54 square miles in the upper watershed, impacts 16 miles of downstream that could potentially be recovered as far as trout fishery goes, or we should say recreational fishery, if we were to manage some of the problems that are sourced from the upper watershed. There's a very good report from USGS that looked at a lot of the discharges in this particular region, also looked at some of the groundwater conditions with respect to underground mine pools. There's already been work, and I saw John Dawes out in the hallway, and I said, you got the Super 7, but we got the Big 9, right? So the Big 9 have already been identified as some of the largest, most significant discharges in the watershed. The black line here is that same purple boundary. So now we're focused in on just the upper watershed. These gray regions are the different towns in the area strung together along PA 61. And the discharges tabulated somewhat in an upstream to downstream location. So the flow is coming from Mount Carmel through Shamokin on its way to Sunbury. The coding as far as the SR dates all the way back to Scarlift days as far as assessments. And even though there's the Big 9, you can see that there have been identified many, many discrete discharges in this particular watershed. And we've heard a lot of numbers out there as far as like these, these big high flow numbers and stuff. If we just sit right on Scott Ridge, and that Q is the algebraic expression for flow, and the subscript 50 is the median or the 50th percentile value of Q from the 12 measurements that were collected most recently. So 50% of the time it's less, 50% of the time it's more. Each one of those discharges represents almost its own major significant project, right? That's the typical condition. We're not going to the design condition just yet, which is going to be a much bigger number to account for some high flow conditions. So just show you some pictures of these to get an idea. So every one of these discharges is sourced from an underground mine pool that is in itself an extremely complicated hydrologic unit. And they present themselves in different ways. In this particular case, they present themselves as these artesian pools that in the area of Scott Ridge, there's a couple of them. They've put a weir plate. They've done some monitoring up there, and to come up with this median flow of 6,200 gallons per minute. There's an aerial photograph of the Excelsior mine strip pit overflow. And so as the name implies, it was a big strip pit that was abandoned that over time flooded up to a certain point where it breaks through and comes down. Now they have a weir there also for flow monitoring from that particular discharge. So here we have this fairly large pond, if you will, as far as the expression of the mine pool. And then there's the Henry Clay Sterling mine. This is another Sterling mine pump. So this is like the top of the pump house where they would pump water out to dewater the workings to get at the coal. Turn those pumps off. Water is up, flooding out of it, turns the corner, and goes directly into one of the tributaries of Shamokin Creek. They might have tried to have a weir plate on it at one point, but it's no longer there. And then finally, one of the more downstream discharges, this is Cameron Drift. It's right on the creek, right? So it's physically, you're looking at a really challenging situation to sort of control and capture that discharge. And so just wanted to show a couple of these pictures to show the different ways they present themselves. And then look at this whopping number, Again, we've heard big numbers in these talks. The sum of the big 9 is 22,000 gallons per minute, 50th percentile value, right? So you're designing much bigger than that. So we're going to get to what a recommendation as far as how you might approach something this challenging. And then so flow is one thing, but the other thing is the loads, right? The contaminant loads. And so load is defined as the flow, Q, times the concentration, C, where that concentration could be hot acidity, iron, aluminum, manganese. Those are the big ones that we're looking at, multiplied by a bunch of conversion factors, and then binned to do the statistics on the load values themselves to represent what I'm going to show. I'm not going to show you all the statistical breadth of these things. I'm going to show you load values, say, for iron at the 50th percentile. So half the time it's more, half the time it's less. So if we just look at 50, and thanks to Bobby and EPCAMR, in the sampling strategy, they did upstream, downstream locations on the trib or the main stem for each discharge. So we have a location that is downstream of the discharges. And what we can see is that the water flowing out of the upper watershed is primarily mine drainage, right? 22 over 28 times 100% as far as how much of that is sourced from these mine pools. The big 9 are producing 5,300 pounds of iron a day, typical conditions. And then we have aluminum, manganese, and hot acidity. We'll talk about each one of these. And I'm going to argue that the big issue is iron, that the iron load coming out of these particular anthracite discharges into Shamokin Creek is the biggest problem that has to be addressed. Now, at that location that EPCAMR sampled, we see that it's dropped to 3,700 pounds per day flowing downstream. Why? Because of the iron-coated streams that are in between the emergences and that particular sampling location, right? So we're seeing pounds of this stuff being deposited in the streams before it goes, before it flows below town. With respect to TMDL standards, so there's, there are different permitting structures. TMDL, total maximum daily load, for these particular contaminants. In the case of iron, well, to sustain a recreational sport fishery, you could allow 100 to 500 pounds to pass town. And then the downstream condition could assimilate that pollutant load. And we see, 3,700 pounds. So this is why we have that red stream all the way to Sunbury. In the case of aluminum and manganese, they're not the primary problems. There is some assimilative capacity for both of those particular metals. And then what I would argue is when you run these treatment plants and are precipitating iron oxides, they are going to absorb manganese along the way, and we can take care of the manganese as we go. And then finally, when we look at acidity, so the operational definition is this hot peroxide acidity. And so in that particular method, what we see is that indeed the sum of the big nine are net acid, has a positive value, net acidic. But if you see the next number over, downstream of town is a negative 1,300. So that negative means that it has positive alkalinity, right? So there are natural sources of alkalinity coming into that system that are taking care of the alkalinity downstream of town. So again, it's a managing the iron load out of these systems. So we'll go back to our upper watershed map, zoomed in just a little bit more, and I'm going to sort of discretize spatially where these different contaminant loads are coming in, right? So now we're looking at just the iron load, subscript 50. So this is the median value. And what we see is that Scott Ridge and the Excelsior Mine strip pit are the largest sources of iron into this particular system. And they're both located a little downstream of Coltmont. Scott Ridge discharges to Quaker Run, and Excelsior Mine strip pit, you saw the picture, that's directly into Shamokin Creek. I thought I was going to use that little laser, but with respect to hot acidity, the good news is that 2 of our discharges are actually net alkaline. And so what's interesting is if you look at the historic data, Henry Clay Sterling mine pump has flipped from a net acidic discharge to a net alkaline discharge. This is one of these important things of long-term monitoring and synthesizing past reports and things like that. So 2 of our big 3 have negative values of acidity loads, which means they're positive sources of alkalinity. And the largest source of acidity happens to be this Cameron air shaft, which I didn't show a picture of it, equally challenging physically as far as that thing is located right next to the creek. So, we have the big numbers. Now we got them spatially, examined. Now let's look at it as a function of time. And what I would start with is the rain. So we're going to look at precipitation as a function of month, and then we're going to look at discharge from the AMD sources. Note that none of these figures that I'm going to show you are on a calendar year. They're on what I call the sampling year. This is where Bobby and the EPCAMR crew started in May of 2023, and the 12th sampling event was April 2024. And at least from this one, the PA climatologist data for Sunbury for that station, what we see is that there was a wet summer, particularly dry November, and then some higher than average rain in winter and spring. So just try and think about, we're going to see other graphs that are flow versus the same sampling year, that we had a wet summer and then a dry fall and then this wet winter. And I'm going to start showing a main stem sampling location. So this is that downstream of town sampling location. There was one further down, but that location was only sampled for 6 of the 12 months. And so this one was sampled for the whole 12. But of those 12 months, there were 3 times when it was not safe to go and do a wading survey across that creek. And so I have pegged that value at 60,000 gallons per minute for visualization purposes, really. And so those are values that were too high to measure. And so rainy summer is not high flow in the creek. The high flow in the creek was those high rains that happened in the winter and the spring. And so the simplest explanation is that soil and plant processes taking up water in the summer are dampening that hydraulic input of the rain in the summer, and you're not seeing that coming out in the stream. But in the winter, when those processes aren't happening, you can have these really high flows coming down the creek. So now we'll switch to a discharge. So this was the one with the really big pond that you could see from the airplane, the Excelsior Mine Strip Pit overflow. Y-axis is flow in gallons per minute. X-axis is the sampling year. The purple line is that 50th percentile value. And then the blue dots are the ones that were measured during that sampling year. And we also have some historical data out there from various reports or different groups that have gone out and measured flow. And what we see from at least this 75 to 2009 period, we have pretty good agreement as far as what was measured this sampling year as compared to times past. And then one of the things that we really got to stress from an engineering standpoint is this idea of a peaking factor. Now, some people might define this as Q max divided by Q min. I'm defining it as sort of like the maximum flow as compared to typical conditions, right? So the Q max divided by Q50. And what we're going to see on all of these discharges is they have a really high peaking factor. So then it's like, well, how the heck do you plumb these things when they have such a range of flow conditions? What I want to do, though, is compare discharges. Let's look at these temporal patterns. And the easiest way to do that is essentially normalize all these data. So for each discharge, what I'm going to do is I'm going to divide it by the maximum value that was observed in those 12 events. So now I have a scale that's no longer numeric with respect to gallons per minute, but it goes from 0 to 1. 0 is no flow, 1 is the max flow value. And if you look at the blue lines, they're identical in shape because they've just basically all been divided by this number. And you can do it for every one. So the gray line, I apologize, it's hard to see, but there's a gray line in here. And it has a couple of these spots where it's hitting the top. That was where I was setting it at 60,000 gallons per minute, right? That's the too high to measure flow in the stream. And what you see is very good correspondence between the discharge coming out of Excelsior Mine Strip Pit and what's being measured downstream of town, right? Suggesting that, and consistent with, you know, if 22,000 gallons per minute is mine water passing the town that's discharging at 28,000, that the mine pool discharge is what's really pushing out the flows. And again, wet summer, right? Wet summer, but we're not seeing high flows in the summer. We're seeing it when those soil processes are off and we're peaking during winter and spring. Scott Ridge, you got to deal with Scott Ridge. It's the largest iron lode in the system. It's the largest flow of all of the discharges. Has a lot of historical data. There have been pilot studies. There's been a lot of other groups. That weir has been used by others, let's say. And so I've taken all of that historical data and binned it out to the month that it was recorded so we can kind of see how it matches our sampling year. And you see there's actually, in this particular case, quite a bit of inconsistency with what we observed this year. But again, low flow in the wet summer and higher flows in the winter and spring. And then finally, the Henry Clay Stirling mine pump. I taught a class last spring, and students designed these different treatment systems for these different discharges. And every discharge had at least 5 words associated with it as far as the name of it. And the Henry Clay Stirling mine pump had some flows that were higher than anything that had ever been recorded before. Almost 18,000 gallons per minute coming out of this thing in April 2024. And other events that were over 12. So compared to the things that were measured in the past, something's happened, or we just had a very different hydrologic year. But there's also this high, I'm going to come back to this peaking factor when I talk about the mine pools. So in this case, the peaking factor would be defined as like 18,000 divided by 5,000. That numerical value, that peaking factor, is higher for Henry Clay than any of the other discharges. Okay, and then finally, since we have them all normalized, we can look at all of the big 9. 2 of the big 9 were only sampled 6 of the 12 months. And 1 of the big 9 had a more erratic pattern. But 6 of the 9 all show this sort of thing where relatively low flows during the wet summer and then some peak flows in winter and spring. Likely related to mine pool conditions. So if we look for named mines from Pennsylvania mine mapping, we will see that the whole upper watershed, except for a few regions, has essentially been mined. But the map view does not convey the complexity of this particular system. The Western Middle Anthracite coal field is this enormous canoe, incredibly folded. I think Steve Matica was saying that there are mine workings that are below sea level in that particular watershed, that that they're 1,000, 1,500 feet below grade, and multiple coal seams that are in this canoe that have been worked in ways to take advantage of shared drain points, or possibly take advantage of shared pumping, or mined out later and unintentionally connected in different ways at different levels. So that plan view of those colored polygons just doesn't represent the complexity. And I was talking to Heather at lunch. I'm like, the remediation of this system could be as complicated as landing on the moon, as far as, because you don't know everything that's beneath you. But I heard Bobby talking about the 3D mapping of the anthracite coal field, and man, that would help us a lot. So same USGS report, or no, this is another USGS report that was looking at groundwater modeling in the system and came up with this idea of an MCU, a multi-colliery unit. Basically, different mine workings that have been interconnected, okay? And the conclusion from that report was that 5 MCUs sourced all the big 9, but sourced the majority of the outfalls in the watershed. So in our report that we gave to SCRA, we discretized it a little differently and said, you know what, there's actually 8 mine pools. And the difference is in this center region where there had been 5, there's some overlap and differences in elevations of 20 years of historical mine pool monitoring data, which I'll show you, where the mine pool water elevations have been measured for 20 years. And so our assessment was that this isn't all one, that these things are actually discrete from one another because those mine pool elevations are fairly stable over, at least you'll see it from 1983 to 2003 when all of this monitoring went on. And the difference between 5 and 8 is actually important because when we get to the idea of hydraulic control, capture, and conveyance, if it's a separate mine pool, you need a separate pump, you need a separate you need a separate line, etc. So our assessment is that there are 8 of these. So Todd Wood from DEP sent me the Excel file that had all of the Western Middle Anthracite borehole monitoring data. And this one is called borehole number 55. It accesses the Excelsior mine. And you see this fluctuation, in some cases 20 feet over the year. And I'll show it to you on a monthly basis, but you'll see that it's high in the winter and low in the summer. And for years they did it quarterly. So for years that had all 4 quarters, I'm showing lines for each year, and then I did medians, so the 50th percentile value of the elevations, and you get what I call the smiley face, right? It's high in the spring, low in the summer, and coming back high in the winter. So similar to what we saw with respect to those discharge patterns. So again, a relationship between precipitation, mine pool elevation, and AMD discharge. You got to work all that stuff out. But I wanted to also add in the borehole that was in the Henry Clay pool. This axis doesn't span 40 feet. It only spans 10 feet. And the measurements are within like 2 feet. There's very little movement in this mine pool. It's almost like that concrete structure is at the mine pool elevation. There's no storage behind that thing. And so when the flow gets going crazy, it just comes roaring out of there. And so again, it's potentially a simple explanation for why this discharge has such a greater peaking factor than the others, right? And so we need to figure this out for every one of them. Okay, so let's get into that. So our recommendation to SCRA is that let's focus upstream of town, because it's more than just getting clean water into the creek and bringing the fishery back. There's social and economic recovery that we want to happen as well. We want clean water flowing through town. So if you have a restaurant and you have a patio and you're looking at a clean stream. And again, the flow is heading this way into Shamokin, through the gap, 16 more miles. Maybe we restore all of those 16 miles as well on its way to Sunbury. And it's maybe ahead of the game, but we're calling this the Coltmont Mine Drainage Treatment Plant. So you got the city of Shamokin, Coltmont here. I'm going to show you some aerial photography where there's a wastewater treatment plant in Coltmont. These 4, and I'm going to also show you pumping distances and elevations and stuff like that. These 4 are proximate enough that we could consider combining them into a regional plant. We focus, though, on Scott Ridge and Excelsior because then we got the 2 largest iron loads in the system coming into one plant. We add the Maysville mine borehole MCU because it's net alkaline, and blend them all together. And now we're talking about an alkaline water to treat. All we got to do is oxidize the ferrous iron. It's going to be a heck of a lot easier. Look at some of these numbers though, right? 12,600 GPM median, right? That's the 50th percentile value. But we could remove 3,000 pounds of iron a day. Super high level, right? I'm not committed to these conveyance routes. I simply said, let's string them along roads and hope that we can get, property owners that are willing to share utility accesses, right-of-ways that are already there. And so just stringing these together. And so we're going to talk about, again, capture, control, and conveyance. So you would have an extraction well to capture the mine pool. You'd have to figure out, like, well, what water elevation do we need to draw that down to dry up that discharge? There's your control. And then you got to convey it over to the treatment plant, right? So all of these things have to happen. So I'm showing you this on the map again. And we are calling this the Coltmont Mine Drainage Treatment Plant. And it happens to sit right above the Maysville borehole. So at least one of our, if we can get 4 into this plant, one of them we're sitting right on top of. So we can, very short conveyance there. We like, you heard the talk about Blacklick. You heard the talk about the Little Conema. We like plant locations to be near a wastewater treatment plant for a number of reasons. Number one, stream discharge location. Number two, you got all the utilities going to the plant, right? Like all that stuff is already there. And so, if we can put a plant here, we can take advantage of some of those things. There's also the possibility of operator sharing. You might be able to man that plant with other people from the other utility. So again, capture, control, convey. I'm an environmental engineer, water chemist, process engineer. The treatment plant is not the challenge. If I know what the flow is and I know what the solids is, I can design a treatment system as far as clarifier, that kind of stuff. We can do that. The thing that is site specific every time is who's going to give me the land? Whose land do I have to cross to convey that water there? So here I'm just showing, like, Scott Ridge, is it a wet seal or is it an extraction pump? So you have to be able to control it. You're going to then have to, convey it over to your treatment plant. But you have engineers to do that sort of thing. Still, it's a big challenge. I wanted to show these numbers here just to go back to those traces on the roads, okay? So we're looking at, 3-mile conveyance line, mile conveyance line kind of thing. And then I'm also picking elevations here that are differences between the mine pool elevation, and you're of course going to set the pump lower than that, and the surface elevation of where we think this Coltmont mine water treatment plant or mine drainage treatment plant is going to be. So there are, in the case of Scott Ridge, we might be able to wet seal and gravity drain that right into the plant. But there are others, like that Maysville that you're sitting above, that's going to require a fair amount of head that you have to bring that into the plant. So these are factors that would have to be worked into design. And, just taking Corbin, for example, you would have to factor in whether capturing that discharge is worth the money that you're going to pay to pump it and convey it over to the plant, right? So these are decisions that are made in like the next phase of the project, right? You have to work the numbers out to make the decision. We can do some relatively simple blending calculations where we take the flows. In this case, I'm showing the 90th percentile as a candidate for the design of the plant, the capacity of the plant, as compared to the typical. And then we have the pHs, and then we'll just take the concentration times the flow, blend them into the combined flow, and we get the highlighted number at the bottom. The important thing is we would end up with a net alkaline water with essentially all ferrous iron, some high manganese, not a lot of aluminum. So if we oxidize the iron, make the red rust, we hopefully absorb the manganese to it. And so the treatment of this is, again, relatively straightforward. The biggie, though, is this number. Right now we're talking 26,000 gallons per minute. And that's a negotiable, that's something you work out with DEP and others as far as how should we spec the design size of this. Okay. Not going to show you process diagrams or anything like that, but it's not just managing the water. Infiltration is a big issue. I think I'm attributing this correctly to Chuck as far as the photograph. Dan Corey, okay. So remember the canoe shape, and it has multiple coal seams. And then some of these coal seams are coming to the very top edge of the canoe, running right down the mountaintop. And people have gone in, I've heard coal miners say, a good coal miner doesn't leave any coal behind. And so if you are going to do that and get at these things, you're going to lead to these crop falls, these subsidence areas so now in the canoe of the upper watershed, you have infiltration at the very top, but you also have leaky sections at the very bottom. So you can get losing and gaining streams. We care about losing streams just like we care about crop falls, because they are going where? To the mine pool that we are pumping out and treating. So you got to have a holistic plan. You got to reduce infiltration as well, because then maybe we're not at 25,000 or 26,000 gallons per minute sort of thing. So the USGS in their subsurface modeling report discretized the whole watershed. This particular boundary here is the Shamokin Creek. You don't have to worry about the scale so much, but green means that segment discharges the amount of water that it's receiving, essentially. So it's on a even water balance. If it's red, it's a losing segment, and if it's blue, it's a gaining segment. And what are the blue ones? The big mine pool discharges, right? They're where the big 9 are located. The red are these parts of the watershed that are known to be losing flow. So we know spatially where to go with respect to focusing on stream sealing, infiltration at the bottom. The crop lines, now I think about drones and using temperature sensors and other things. We should be able to completely map out all of those crop falls as well and go and start sealing those things up. So Tetra Tech did a separate report. So this is the watershed assessment report. But previously, Tetra Tech did a big refuse stockpile investigation and found lots of refuse in that particular area. There's a project ongoing with respect to Big Mountain, but any of the sort of refuse that could be addressed is going to improve surface water runoff. There's also some ponds that are probably very much like leaky streams that should probably be assessed as well. So there's these AML features, abandoned mine land features, different than all of the AMD stuff that I was talking about. Okay. So in the summer, the big 9 are 100% of the water going downstream of town. And most of the time that's 85% or something like that, right? So the big 9 are a huge source of water to Shamokin Creek. We've identified that Scott Ridge, Excelsior, and Cameron Air Shaft are the largest loads of iron. Cameron, again, this is the most downstream one, was the largest load of acidity. And again, getting back into the engineering side, the peaking factors on these things are really going to be tricky as far as how you're going to handle conveyance of things that might go from 1,000 to 18,000 gallons per minute. And so that's kind of why I'm excited to work on this project. We think there's 8 mine pools instead of 5. And again, it does matter how many you think there are with respect to control. And those 8, we talked about the big 9, but those 8 actually have 20 AMD sources with them. And so you start controlling those and you get more than the big 9, depending on where you put that so-called water control, mine pool control elevation. You know, we've seen these high fluctuations, which is good, which means we have storage if, you know, we have to do maintenance on the plant or something like that. But we saw others like Henry Clay that appears to have no storage. And then this is the future work. You really have to nail down all the, you know, in fine detail, the relationships between precipitation, mine pool elevation, discharge, probably at an incredibly good temporal resolution to have a strong confidence going forward in designing a plant. And I will end it there, and thanks for hanging out through the talk. Happy to take any questions.
Discussion about combining mine pools using pipeline or underground drilling. But in this talk, you were showing, I'm guessing, surface pipeline or pumping at each of the separate mine pools individually. Is there a reason for that? Because this is the anthracite and it's so steep that combining those mine pools together is going to be more challenging in this region? Or is it,
No, I would say it was a preliminary conceptual decision. I'm waiting for Bobby's 3D model of the whole thing. Now, I do know, so in that report, there's a report about, or there's a section that's on mine pools. And a good majority of it is like the mine pool elevation of the Greenall mine is, you know, tends to be this. But there's other descriptions say that the Greenall mine connects to mine B at 850 feet, but it connects to mine C at 750 feet. And so when we talk about it as an MCU, there's a lot of different connections. And why is it at different elevations? Because that plan view of that map has multiple walls of that canoe in it. And so the MC, if you could convey some stuff underground, that would be advantageous. I didn't feel confident, you know, like suggesting that, and just wanted to at least lay out some more standard approaches to it.
The last time some of the data that was collected for borehole elevations in those regions of the mine pools was maybe 15, 20 years ago. So and there's lots of other pumping that has continued or stopped since then, and nobody has gone out yet to collect the data or put in place some of the recommendations that have come out of the report for future installation of pressure transducers and things that will get us real-time data, that will get us the rainfall to match up to the data for the sensors. And when we do that, that'll be advantageous to have. And then also years ago, when we finished up the report with USGS and did some of the previous work, we didn't have the mind maps and the mind map inventory yet that now has been done by us and other universities across the state, but particularly us doing the work in the anthracite region, that we have every vein now from the surface to from 15 veins beneath the ground, that these rock tunnel interconnections that he's talking about, we could now see in potentially in 3D, but we're trying to map that and understand that better to show what those connections are. The only way we're going to know that is to actually get the borehole data today. Kind of like
Today.
water quality.
Yeah.
Today in flows.
Right. I saw Scott Mays talk, and I was just like, oh, us, like you or you guys need those things in multiple locations. So I wanted to bring this map back because the MCU, one of the MCUs is the Scott. So this is Scott Ridge. The Scott Ridge, I think it's just called the Scott MCU. And it supposedly includes Richard Shaft. The elevation of Richard Shaft is far above the mine pool elevation of Scott Ridge. So if you start pumping that thing, what's going to happen to Richard Shaft? So even the MCU concept needs some ground truthing, and these sorts of monitoring stations that Bobby's talking about is the first step. All right, it looks like we're done. Thanks for your questions.